Minutes to welcome everybody. Clayton, Fabio, and Lindsay. Lindsay and I have organized this workshop, have contacted you repeatedly, I've annoyed you with demands and requests, and we benefited from the support of the program organizers, especially Catherine, who is opening the workshop today. So thank you so much, and I had to make some difficult choices this week in terms of dinner at Trinity College, the formal dinner, in terms of wine, and I hope you won't blame me on that part. But anyway, so please enjoy the workshop, and we can now start with Catherine.
Okay, thank you, Serge. So on behalf of the program organizers, I'd also like to thank the workshop organizing committee, Serge, Fabio, Lindsay, and Clayton. And also for scheduling me first. If you're here expecting to see Roger Gannam, I'm sorry to say he's cancelled, so I am in theory the replacement for Roger Gannam. So here's the title of my talk. If you're a statistician sitting there thinking, what on earth has this got to do with surrogate modelling, I will try and explain that as I go along. So we have a 6-month program here on uncertainty quantification, and the main aim of this program is to try and bring statisticians and people in the applied math community, including numerical analysis, together to have a meaningful dialogue about uncertainty quantification, to learn from each other's methods, and to try and work together going forward. So in the first workshop, which was 4 weeks ago, speakers were asked to talk about some of the key methodologies that are used in our respective communities. So we had talks on things like Gaussian process emulation and things of that nature, and the analogues in the applied math community. So what I'm going to talk about today, in terms of method, is something called the Stochastic Galerkin method. These are families of schemes that we can use to approximate solutions of PDE models with uncertain or parameter-dependent coefficients. So a frequent question I got in the week after workshop 1 is, why on earth are all of the applied mathematicians obsessed with elliptic PDEs? Okay, so I'm going to try and answer that question, but the short answer is we're not really interested physically so much in solving elliptic PDEs, but when it comes to theory, we're very cautious people, and elliptic PDEs are really the PDEs that we understand most about. So when we're testing out new methods, this is usually our go-to model to start, to try and understand what's happening theoretically with our new methods. So my first few slides are intended to be quite introductory. There are going to be several talks from the numerical analysis community this week, which will have words like adaptive and stochastic Galerkin and elliptic in the title. So I hope that through my talk, being quite introductory in the first half, will lay down some of the groundwork for some of the other speakers later in the week as well. Okay, because it's important that we do all understand each other and learn to sort of talk each other's language. So I hope I'm getting a bit better at that, but you can tell me afterwards whether I've been successful or not. So let's deal with elliptic PDEs first of all. Why might we want to solve elliptic PDEs? Well, it's a very standard model. It's usually a building block in more complex multiphysics models. We typically use the elliptic PDE to model things like steady-state heat diffusion. In workshop 1, it was often called a groundwater flow problem, so let's try and deal with that. So a very simple physical model for the flow of fluid through a porous medium is described by this key equation, which is called Darcy's law. It relates the velocity, v, of a fluid to the gradient of the pressure, u. Okay? And then we might have some other equation which says something about the divergence of the velocity. If we need to conserve mass, then we set f to be 0. Otherwise, we might have some sources and sinks, in which case f is not 0. A key thing in this model is this a that I've highlighted in red here, which will be, it contains many things, but in particular it depends on the permeability of the medium through which the fluid is flowing. So typically, in an engineering type application or an oil reservoir type simulation, we wouldn't know what A is everywhere, right? We wouldn't be able to measure it everywhere in space. We might have a few data measurements from borehole measurements, but we typically would not know what it is everywhere in our spatial domain. So what's done typically in our community is to model such things as random fields. And this is the kind of notation that we use. Just to be clear, x is not a set of parameters. X is a point in space. Okay? So in many statistics talks, it's the other way around. for us, x will always be a point in our computational domain D. So what you're looking at here are two draws, two realizations of a Gaussian random field. It would not be appropriate to model A here as a Gaussian random field. Right? Permeability should be something that's positive. Okay? So you will hear talks later on in the week that are not using Gaussian random fields here. They might be using log normal random fields, so that we can ensure that these things are have positive realizations. Okay, so there'll be lots of talks about this week, I imagine. So the idea here is you decide what kind of random field you want to put in this problem. You'll typically have to choose a mean function, the covariance. So this is a covariance function for A. And then, given that information, we want to propagate that information through this PDE model and estimate some quantities of interest related to the pressure and the velocity, which will also be random fields. So, mathematically, we'd set up the problem like this. If you don't understand this notation, don't worry about it, but you'll see notation like this. Associated with this problem, we'll have some probability measure, and it will all seem quite abstract. So then what we typically do is we come along and say, okay, I'm not just going to deal with some abstract random field, I'm going to make some more assumptions about this thing in my problem that I'm uncertain about. So a key assumption for many of the methods that you'll hear about in the applied math and numerical analysis community is the assumption that actually this isn't sort of random or uncertain in a sort of completely unknown way. We're going to assume that actually this random field is a function of a set of random variables. So here I've written a collection of m random variables. We typically call these xi, and we might collect these into a vector that we call xi. So we're going to assume that the way A is random is through its dependence on a set of random variables, and you'll typically see us use expressions like this. So the input to our PDE might be an expression of this form. Okay, so we'll typically have a leading term which is deterministic or parameter free, and then we have this term here which is a function of these random variables. So that's the kind of expression that you'd see if you use some kind of Kahuna-Lurv type expansion of a random field. Or you might also see expressions like this. So instead of just having xi's here, we might have some functions of all of the xi's here. For instance, these might be polynomials in these variables. Okay, so we'll assume that we have some structure in the randomness, if I can say that. We'll assume that the input to our PDE model is some function of a finite set, or later on it will be an infinite set of random variables. Okay. And then, okay, typically what we do then is something, well, this is a bit hand-wavy, but we typically stop talking about random variables and start talking about parameters. So if I'm assuming that the input to my PDE model can be represented through these coordinates, through a set of random variables, if I can show that the solution to this problem is also a nice measurable function of these random variables, then I can rewrite my solution in terms of these variables as well. And that's typically what we do, we just change variable. It's a bit more complicated than that, but a lot of people will be presenting talks and they'll say that they're solving the elliptic PDE depending on a set of parameters. So we've got a parameter dependent problem. So I apologize to the statisticians. Theta is not a hyperparameter. So I used to use y's for my parameters. That was confusing. So I changed them to thetas and it's still confusing, apparently. So just to be clear, theta here is going to be a parameter. Okay? These are parameters that enter my problem. Usually we're thinking about these as being images of random variables that characterize our input random fields. But what we can do when we do this change of variable is, instead of writing down this problem, which is posed on a rather abstract sample space with a rather abstract probability space, is to write it down instead as a problem which depends on a set of parameters. So theta now in red is a vector of parameters, and they'll take values in some set, which I'll call gamma. That's typically the notation we use, which will be called our parameter domain. So we've got a PDE model, and we've got inputs A and the output U, which is both a function of our spatial coordinates and a function of these parameters. Okay? So many of the talks will say they're solving parameter-dependent PDEs. Okay? So that's what we're going to do. But I want to make it clear what I'm not going to do here is do inference on these parameters. You could do that, right, to solving an inverse problem, but in this talk, the idea is we're given information about A, We make some assumptions about these parameters. We assume they're related to random variables with a particular distribution, and then our goal is to estimate U given this information. I am not trying to do any inference here to determine these parameters theta. Okay, just so we're clear, what does a numerical analyst do if faced with this problem? Okay, just so you know sort of our mindset and why we obsess about the things that we do. First thing we do when we're given a PDE model and it's got inputs that depend on a set of parameters, first thing we worry about is, does a solution exist and is it unique? And in order to get that, then we'll typically have to make a lot of assumptions on the kind of A that can go in here and the kind of parameters that we can have. So for example, as I said before, if these are Gaussian random variables and this is not the right kind of function, then I'll easily be in trouble and not have a unique solution, or any solution. Once we've established that a solution exists and is unique, then we'll worry about how smooth that function is. Is it well behaved? Is it a nice function of our parameters, and so on? And then once we're happy with that, and we understand how the true solution, that we can never compute, but how the true solution sort of behaves, then this is the sort of thing that is occupying most of our time, is trying to develop approximation schemes for the solution to this problem that are stable, that converge, and here's the kicker, that do not suffer from the curse of dimensionality. So we don't want our convergence rates, ideally, to depend too heavily on the number of parameters that we have in our problem. And if we have infinitely many parameters, we definitely don't want them to depend on the number of parameters that we've got. Okay? Once we've done that, we want to know about the error in the approximation. We also want to be able to compute errors. Of course, the true error is not something that we can actually compute. So actually, we'd also like to develop what we call a posteriori error estimators. So we'd like to be able to compute something. We don't just want the approximation to our problem. We then want to know or estimate the error associated with the prediction that we've made in a computable way. That's called a posteriori error estimation. And we need these error estimators if we're going to be able to construct approximation schemes adaptively, which is what my talk is going to be about. Can't do adaptivity unless you have an a posteriori error estimator, or at least you can't do it well. And then somewhere along the lines we worry about linear algebra as well. Okay, so elliptic PDEs, this is done, we're all still trying to do this. We can do a bit of this. This is sort of where there's still some work to be done. Because if we really want to do this and combat the curse of dimensionality, we need to do things adaptively, and we can only do that if we have a posteriori error estimators. So every time we come along with a new PDE, yes, we can absolutely do numerics with the kind of scheme I'm going to talk about for more complicated PDEs, but when it comes to actually trying to understand the errors in what we're doing, then I'm afraid at the moment we're all still mainly talking about elliptic PDEs. Okay? At least at this workshop. Okay, so there are a huge number of people who have worked in this area, and I just want to highlight a couple of people who are here visiting the program who have worked and done a substantial amount of work in this field. So there's a large body of literature on approximation theory for solutions to elliptic PDEs with coefficients, as I've described, that depend in some way on a set of parameters. So I've highlighted in red names of people who are here. I've probably forgotten some people, so I apologize if I've forgotten you. So Christoph Schwab, who will be speaking later today, who's over there. Ron DeVoe, Albert Cohen, who will be program participants later this year. Who else have we got? Fabio Nobile, Raul Camponi. Marcus Bachmeier was a speaker in workshop 1. So some of these people are here, and if you want to know more about the underlying approximation theory, you should definitely talk to them. But here's what I'm going to do, okay? So let's just, let me emphasize what it is I'm trying to do. I've got a coefficient in my PDE which depends on a set of parameters. So given some information about the form of the dependence on the parameters, my goal is to approximate, to find an approximation to the solution to this problem, which I'll call U hat. So that thing is a function of our spatial coordinates, and it's a function of the parameters that define A as well. So how am I going to do this? The basic method that underpins what I'm going to talk about is called stochastic Galerkin approximation. We didn't hear a lot about this in workshop 1, but over the last couple of weeks, program participants have been talking a bit more about this method. If you're a statistician, you might know it as the intrusive polynomial chaos approximation. Well, one form of it could be called that, so I'll say something about that later on. This is quite a general approach. How we implement it is our choice. So I'm going to use finite elements for the spatial part of the discretization, and I'm going to use orthogonal polynomials for the parametric approximation. So SGFEM just stands for Stochastic Galerkin Finite Element Approximation, and I'm going to talk about how we do this in an adaptive way. The thing that's driving the error estimation is a scheme. So this part is joint work with David Sylvester, who's also here somewhere at the back, and Alex Besvelov, who's also here at the front. Okay, so if you want to know a bit more about this, you should talk to them as well. And then I'm going to end sort of looking forward to a more complex version, which I'm not going to say too much about here, multi-level adaptive stochastic Galerkin finite element method, and just give an advertisement for Adam Crowder's poster. Adam is my PhD student. He's also based in Manchester. And if you want a lot more of the gory details about this, then you can talk to him at the poster session. So that's the plan. Okay, a couple of other basic things you need to know if you've never met these kind of schemes before. So there are many families of methods that collectively are called stochastic finite element methods. So in PDE setting, engineering applications, we like finite element methods. So we're typically using finite element methods to take care of the spatial discretization. How we deal with the fact that our solution that we're trying to estimate depends on a set of parameters that may or may not be connected to some random variables, well, that opens up a lot of choices. So obviously we could do Monte Carlo, and I'm not sure whether there'll be any talks this week about Monte Carlo, but you'll certainly hear multi-level, multi-fidelity, multi-index ideas in a sampling context. I'm only talking about one way to solve this problem. There are many others. Stochastic collocation finite element methods, reduce basis finite elements, and so on. So what's tough about doing this in the stochastic Galerkin setting? The kind of approximation that we're going to come up with has this form. So ultimately we're going to solve a problem, we'll get these things in red, and what we'll have at the end of the day is this. Okay? We're going to pick some functions of our spatial coordinates as basis functions. We're going to pick some functions of our parameters as basis functions, and we're going to look to approximate our solution by sort of a function which has this form. So nx here will be the number of these functions I have, and np will be the number of these functions I have. So the problem is the size of the problem that we have to solve. So if I put no thought into how I choose these things, this thing can become large very quickly. Okay? So it's much more challenging to implement than sampling methods, say. Okay, so the first part was to just quickly review how we build a stochastic Galerkin approximation. So here's a PDE again. So on this slide, I've just highlighted in red the things that depend on the parameters. So here's my PDE. Obviously, I'll have some boundary conditions as well. I haven't written those down. And now I'm going to make an assumption about the A that's in this problem. Okay? So this could have started life as a random field. I'm just going to think about it here as a function of a set of parameters. So in my talk, the A here is going to have a first term, which will be parameter free. So this could be the mean of the random field. And then the other part of it will be an infinite sum. And inside here I have parameters. Okay? Parameters which will be associated with some distribution that I will pick. The first key assumption that we need is this. So this is an elliptic PDE. To establish existence and uniqueness of a solution, this is a key thing that we need. Basically, this says whatever I put in for theta here, whatever functions I put in, so whatever point x I put in here, I would like this always to be a positive and bounded quantity. We need that. So, what does that mean practically? If I don't pay attention to this, it's quite easy to put in some parameters here which violate that assumption. So our starting point is to make sure that we put the right assumptions on these thetas and the right assumptions on these functions in order to guarantee this. So not only will these parameters need to be bounded, these functions, in terms of their norms, will need to decay sufficiently quickly compared to the norm of this term. But I won't get into that. So what do we do? Here's our PDE model. Okay. If you don't understand what this means, don't worry about it. It's not all that important. Well, it is, but you don't really need to understand for what I'm going to say. Let me put it that way. So we're going to look for a weak solution to this problem, which will have to belong to a certain space. I'll have to get the space right, so it's absolutely important. What do? We multiply both sides of this function by a test function, which I've called v, which again has to belong to the right space, and then I integrate. So this is the weak form of the PDE. This is actually at the heart of any finite element method. The only thing that's different here is that we're integrating not just over our computational domain D, we're also integrating over this parameter domain as well. Okay? This does not mean that we're only solving for the expectation of the solution. That's something that people often say to me. Okay? We're essentially defining a weak form of this problem. So inside here, I have to be careful how I'm integrating. I've got infinitely many parameters. I need a measure associated with my parameter domain, and we do absolutely need to be careful about how we do that. But at the end of the day, I'm just going to hide that away with some clever notation, so perhaps you don't need to worry about all the details. This is the structure of my problem. I'm trying to find a weak solution to my PDE. It lives in some appropriate space, and the structure of the problem is this. Okay, so on the left-hand side, I've got a bilinear form. Over here, I've got a linear functional. And because it's elliptic, as long as this is true, it's nice that I have an inner product here to work with. This helps us a great deal with analysis. Okay, but this space is infinite dimensional, so we can't actually find the solution. This is something we can never compute. So what do? We come along and we replace this space by something that's finite dimensional. So that's the same thing, except I've just replaced u with u hat now, and v with v hat. So the structure of the problem we solve is like this. We're going to find an approximation to the solution to this problem. It lives in a finite dimensional space, and it has to satisfy these equations. This is called Galerkin approximation. That's what we're going to do. Okay, sounds easy. But what am I going to put here? Okay, so in standard method, this is what we do. We're going to look for an approximation in a space that has this structure. So there are two spaces that I have to pick, x and p. Okay, I said I'm going to use finite element, so that just means for the space x, I'm going to choose a finite element space. So ultimately, I have a set of basis functions. Let's say I've got nx of those, and they're associated with a finite element mesh. So my problem has a computational domain, and I stick a mesh on it. The fineness of the mesh determines how many of these basis functions I have. So many of you might have used black box finite element codes. But then I also need to choose this space P. So I need to think about how I'm going to approximate the solution to my problem as a function of the parameters that are in my problem. Okay, and this is typically the notation that's used nowadays in the numerical analysis community. So we could just fix a number of parameters and say I'm going to use polynomials of some fixed degree in those parameters. But remember, my problem here, in theory at least, I don't know which parameters are important in my problem yet. So let me just emphasize that bit before I go any further. I will want to compute quantities of interest related to u, but the a in my problem is in theory a function of infinitely many parameters. When it comes to developing an approximation, clearly my approximation can only depend on a finite number of parameters. So I could truncate this before I start, but if I don't know which parameters are important for my quantity of interest, I'm going to need to learn that as I go. So we need quite an abstract or a very sort of flexible way of defining a set of polynomials, and this is the way it's typically done. So we're going to take a set of polynomials. Each polynomial psi here is going to be associated with a multi-index, and so we're going to take a finitely supported sequence. So if I let alpha be a sort of sequence like this, each entry in the sequence can be 0 or a natural number, and each of these entries is going to essentially tell me a polynomial degree. So J is going to be the set of all finitely supported sequence. So in other words, the number of entries in these multi-indices that are non-zero is finite. I'm going to choose any finite dimensional subset, I'll call that JP, and that set of multi-indices will define a set of polynomials for me. Okay? So when it comes to choosing a set of polynomials, what we actually do is choose a set of multi-indices. So as a quick example, let's say I took this multi-index, so dot, 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 it goes on forever. So it's 1 here, 2 in the third component, 10 in the fifth component. So if I want to define a polynomial associated with this multi-index, what I do is I multiply together polynomials in just one parameter for each of these terms. As long as psi 0 is defined as a constant polynomial 1, then what does this mean? It means this is sort of shorthand notation for multiply together a polynomial of degree 1 in the first parameter with a polynomial of degree 2 in the third parameter with a polynomial of degree 10 in the fifth parameter. So writing things this way allows me to quite flexibly design polynomial approximation spaces. So what's typically done is we choose these univariate polynomials to be orthonormal in a certain sense, and that gives us that these polynomials are also orthonormal in a certain sense. Okay, so that's what we're going to do. We choose x, we choose p. These are pretty standard choices. That's what we're going to do to start off with. And then what you do, you put them together, and then the thing you're trying to find lives in the tensor product space. So how do you get this? Well, you just turn it into linear algebra, and you find that you have to solve one linear system of equations. AU is equal to F. But the number of equations, as I've already alluded to, is the product of the dimensions of these individual spaces. So if you just started with no a priori knowledge, you just whacked down a really fine finite element mesh, you stuck in loads of polynomials, this would really get very big and possibly too big for what you actually need. So just a quick word, as I said, this is often called an intrusive polynomial chaos method. So if you've chosen your polynomials to be orthogonal, like I just said, it's often termed a polynomial chaos method. We have to solve one big linear system of equations. The good news is the matrix has a lot of structure. The K matrices here are associated with one part of the discretization, the finite element space. Finite element matrices are usually sparse. The G matrices, they're associated with this polynomial space that you've introduced. And the good news is if we use the sort of polynomial chaos approach, they're orthonormal. That makes these matrices sparse as well. So in particular, G0, the first term here, is always the identity matrix, and the other G's that sit over here are also sparse. Okay? So I've talked to a lot of statisticians over the last couple of weeks who often say that they're using computer models in a black box way. So is this a feasible thing to do if your model is completely a black box? Well, if you don't know what the underlying equations you are solving, then you probably won't be able to write down the structure of this matrix. If you do know what equations that you're solving, you can often figure this out by hand and learn that actually the matrices that you might need are actually already available to you in your code. So is it an intrusive method or not? It's intrusive in the sense you do need to know your equations. If you can figure out the structure of the linear system, then quite often pieces of the linear system that you need are available to you from the code that you have without intruding in it, if I can say that. Okay, but what you will definitely need always are these extra matrices G that are associated with the parametric part of the problem. And they would need to be changed if you wanted to change the parameters or the distribution, for instance. Okay, you might have noticed I've got M here. So my original problem had infinitely many parameters in it. So why is it finite now? After we've solved our problem by projecting onto this space, this set of polynomials will only have a finite number of parameters in it. It will be a finite dimensional space. So because of the way that the structure in the equations and the orthogonality of the polynomials in here, this will always implicitly get truncated after you've chosen this. Okay? So we're never doing computations with infinitely many terms. Okay? Okay, so you might still be thinking, what on earth has this got to do with surrogate modeling? So let me try and explain. We use this term surrogate in different ways, so that's one thing we might want to discuss this week. Let me just say it again. So I'm constructing a function at the end of the day. I'm doing linear algebra, but what I have at the end of the day is a function. It lives in this tensor product space. I solve a linear system of equations. I get this vector u. This vector u actually defines a function which I've written out here. My approximation lives in the tensor product space. If I write it out like this, I can write it as a sum over all the multi-indices that are associated with the polynomial space I've chosen. I have my polynomials in my parameters, and then I have these coefficient functions which are defined through these entries in this red vector. Okay, so that's what I have when I've done this. So this can be used as a surrogate. So what do I mean by this? I have a functional expression in terms of theta. If I want to query this for any choice of theta, now that I'm done, I can do that. Okay? So all I need to do is evaluate these polynomials. Don't have to solve anything else once I've got this. Evaluate my polynomials at the parameter of interest and multiply by these coefficient functions that I get. So for instance, you might be doing inference, you might be trying to solve a problem and infer some parameters, you might be using an MCMC routine. If you'd actually computed this before you started, you could use this as a surrogate, as a stand-in when you need to evaluate your solution in your MCMT routine, for instance. We do that as well, but that's not what I'm talking about here today. My focus is really on how I actually construct this thing that you can use as a surrogate if you want to. Okay? Because we do have to care about the computational cost it takes us to build a cheap surrogate, right? Okay, so this picture just to emphasize this, what actually you get after you solve this linear system. You have these functions, and if you want to use it as a surrogate, you stick your parameters in there and you multiply by these functions. So these are just what some of these functions might look like for a simple elliptic PDE. So this one's associated with the sort of zero index, so that'll be the leading term in the expansion of your solution, and each one of these terms are associated with a different polynomial basis function. A couple more words about linear algebra. So, okay, I think I'll skip that. But the key thing is, if you just didn't think about the spaces that you're using to generate your approximation, you pretty quickly run out of memory. If you cannot store a vector of length nx times np in your computer, then you can't do anything. You can't solve this linear system of equations. So here's just a toy example, just to show you. So here's a problem where, we just have 2 dimensions in space. This means that my finite element space is bilinear approximation. So my finite element mesh has 65,000 degrees of freedom, which is by no means a tough problem. Let's take a coefficient which has the structure that I said, but this time I'm actually going to truncate it. So let's say there are 20 parameters here. These parameters are associated with uniform random variables. And these terms in here are associated with a particular covariance function. If m is 20, right, so as we said here, 20 parameters, here what I'm doing is I'm choosing a polynomial space. So I fix my finite element space. So my polynomials are going to be polynomials in these 20 parameters. And as I travel down the column, I'm using more and more polynomials. So here I can solve the problem, no issue. But when I get to here, I've got 10,626 polynomials. So my approximation space is the product of these 2 dimensions.
Sorry, what's k then?
So, sorry I haven't defined that. I'm just saying, so by varying this parameter, I'm taking more polynomials. So this is using a very naive choice of polynomials. I'm using polynomials of total degree k in 20 variables. Okay? But that's not important. The thing I just wanted to emphasize is a really big space, right? So if I've done this naively, I'll end up with a really big space really quickly. Multiply those 2 things together. What's that? About 670 million equations or something like that, right? I'm out of memory on my modest university-provided desktop. Okay, so what can we do instead? Well, we can try and do some stuff with linear algebra and tensor methods and all that kind of thing, or we can do things adaptively. So this is what we want. We want a practical algorithm that will actually start with very low dimensional spaces and compute an initial approximation. The trick here is never to do more work than we need for the quantity of interest and the error tolerance we have in mind for that quantity of interest. So let's, if we can, start with some low dimensional spaces, compute an initial approximation quite quickly, estimate the error that's associated with the approximation I've currently got. Right? So we need some measure of error. So the measure for the error that I'm going to use in this talk, and I suspect other people later in the week might use the same measure, we're going to talk about the energy norm of the error. The energy norm comes from the definition of the weak problem and the underlying elliptic operator. The energy norm, E for energy, is defined like this. If you think about it like this, it's sort of like a root mean square quantity. Okay, so of course your quantity of interest might not be this, but this is all I'm going to talk about in this talk. If that's our goal, is to control the energy norm of the error between the true solution, which we can never compute, and our approximation, we need to be able to estimate this. So this is just a number at the end of the day. So we'd like to be able to estimate for a current approximation the error. And then if the error is too big for the accuracy tolerance we have in mind, we need to go back and correct these spaces, enrich them. So we don't just want a number when we do error estimation, we want some information about where we need to put more effort in our computation. Do we need to put more effort in our finite element approximation? Do we need to put more effort in our parametric part of our approximation? Both. And ideally we'd like this to be as automatic as possible. We want an algorithm which essentially will just run with no tuning of parameters that will automatically decide what to do next if my current approximation is not good enough. And ideally the adaptive algorithm should generate a sequence of approximations and then stop. Well, okay, we can never measure this, but when the estimated error is smaller than the tolerance. Okay? So that's what we like. So that once we've done this, what we can do is say our surrogate model satisfies this error tolerance. That's how good it is, right? If you then want to use it as a surrogate. So the thing that drives all of this is the way that you do the error estimation. And there are going to be other talks about this later in the week as well. So there are definitely people in the room that have worked on this already. So Mark Nigel, who's over there, is going to give a talk later in the week. Christoph Schwab, who again has also done a lot of work on this. So this is what I might call the German school of a posteriori error estimation. I'm going to use what I call the Manchester-Birmingham school of error estimation. Okay, so the way we do error estimation, right? The thing that we do differently is the way that we do the a posteriori error estimation. So the approach could be called an implicit approach. So that's to say we compute an approximation to the solution of our PDE, and then to estimate the error, we have to solve another problem in order to estimate the error. So it doesn't come for free. We have to solve a problem. And the payoff you get for this is often sort of it's a better error estimator, but you do have to do more work. So why do I call it the Manchester-Birmingham School of Error Estimation? Actually, at its heart, it's a very classical method that's known to people who work in the finite element community, just adapted to these parametric problems. So this is the paper where it started, 2014. So as I said, this is joint work with Alex Bespalov, who's sitting at the front, and David Sylvester, who's somewhere at the back. Okay, so this is the approach to the error estimation that I'm going to take, and you can find more details in that paper. And there have been a couple of other papers and preprints using the same strategy and sort of developing it in various ways. So this is what I'm going to sort of talk about in a couple of slides. Okay, so I hope the sort of setting is clear. It's going to be a bit more technical now, but I'll try and stress the important parts. So remember, so U is the thing we're interested in. That's the solution to our PDE model. That's the thing we can never compute. But we know it's a solution to a problem which has this structure. So here I said on the left-hand side of my problem, I've got this bilinear form. Now, there's a lot of structure in here because I made a lot of assumptions on the way that my inputs depend on the parameters in the problem. So that structure is inherited through this bilinear form here. We've got one term for each term in the expansion of my diffusion coefficient. And I'm highlighting in red here the thing that's important for the way that we do the error estimation. Okay? So the first term here is associated with the first term. That's the deterministic part, or the part that doesn't depend on any parameters in the problem. So the first part is defined like this. And the good news is that if my problem is well defined, in that I said we need lots of assumptions on the type of parameters that we can use and the functions that appear in the definition of A, otherwise we don't have a well-posed problem. But if we do, then this bilinear form gives us the thing that we call the energy norm, and that's the norm that we want to measure the error in. Okay, so another way of writing the energy norm is in terms of B, where B is the thing that's in my problem. So if I just look at the first term in isolation, we've got a coefficient in there that doesn't depend on any parameters. That's like the mean of your input random field, if you want to think about it like that. And it's advantageous to work with this, because we'll see on the next slide. But this should be physically something that's positive and bounded, and if it is, then this also gives us a norm. And these two norms are equivalent up to some constants. I'm sorry, there are going to be some constants flying around now. So we've got some constants, little lambda, big lambda, that will be important later on. So this is just to say we want to measure the error in this norm, but actually for computations we're going to use this other norm because it's computationally much cheaper to do so, and these norms are equivalent. Okay, so let's just go back again. So the true U that we're interested in solves a problem which has this structure. We're going to estimate the solution. So I'm going to call my approximation UXP now, just to stress that the approximation depends on the choice I've made for x and the choice I've made for p. So that function satisfies this problem. Okay, so what we're interested in is the error. We're interested in the error, which is the difference between that u and the thing that I've actually computed on my computer. Right? So I've computed UXP, I now want to know what's the error. Well, if I just manipulate those equations, we find that the error also satisfies a problem which looks very similar to this problem. But on the right-hand side, what have I got? I've got the residual. So this is the residual error associated with my current approximation. The error, the thing that I want to know about, depends on u, which I don't know, and it lives in an infinite dimensional space. So we can't compute this, right? So I'm not saying we solve this, we just know that the true error satisfies this problem. But this is the basis for doing an approximation of the error. Okay? To get UXP, we discretize this problem by replacing this space with a finite dimensional space. So we do the same thing here for the error. We change this space for a finite dimensional one. The bad news in this context, particularly, and it's much worse than in standard finite elements, is, okay, we're going to have to choose a finite dimensional space here. If we choose the same space that we use to approximate the solution to our PDE, this would be 0. And the only estimate of the error that we'd get is 0. Okay? Galerkin orthogonality tells us this is 0. So we can't use the same space. We have to work in an even bigger space. And given this was already a tensor product space, that sounds really bad. But that's the starting point for the strategy. We're going to estimate the error in a space which is richer than this one. That's the space in which our current approximation lives. Sounds bad news, but there are two key things that we need. First thing, remember I said, what we're going to do is replace b with b0 on the left-hand side of the problem. Remember, this is not in the estimation of u. This is only to estimate the error. Okay? So over here, we're going to replace b with b0. Why do we do this? Because sitting inside here, I have something that doesn't depend on any parameters. The matrix version of this is block diagonal. So this means I can actually solve this problem computationally quite efficiently. And the second thing I'm going to do is be quite smart about how I choose the space I'm going to put here. So notationally, this is where it gets a bit heavy. It's kind of 4 key letters you've got to remember: x and y and p and q. So x and p, you've already chosen those. And bear in mind, I'm not telling you how to choose this. This is quite general. The finite element code I've got might be different from the finite element code that you've got. The choice of polynomials I've made might be different to the choice of polynomials you've made. But you've made a choice for x and you've made a choice for p. You've got your current approximation. So now we need to come along and choose 2 new spaces. We're going to choose a y, which will be some other finite element basis functions, and we're going to choose a q, which will contain some new polynomials compared to the ones you had before. So I'm not going to propose any restrictions on y and q other than these ones here. And then what we're going to do is estimate the error in this horrible looking thing down here. So what is this? So this space has got 2 parts. So this is the space where your current approximation to your PDE lives. So the bit in blue is the thing we're going to add to this space. So what we're going to do, so let's break this down into 2 separate parts. So you're going to come up with this candidate set y, and we're going to tensorize y with the old polynomials that you had. And then we're going to take your new polynomials q, and we're going to tensorize those with the old finite element functions that you had. Okay? And if we mess around with the structure, we realize that actually we don't need to estimate the error in the whole space. We can do computations just by working on this increment space. So what we do, we compute a number, eta. Eta is our error estimator. To compute eta, we just need to know these two terms. So where do these two terms come from? Which is just what I said here. We go back to this problem, we replace b with b0, and we replace this space here with either this part or this part. Okay. So what we have is two sub-problems that we solve. Okay, two problems. At the end of the day, just linear algebra on a computer. So if you're a numerical analyst, you probably know what this means. If not, it's just two matrix problems that we have to solve. But the key thing is, each of these problems is associated with just one part of this new space that I've constructed once I've chosen y and once I've chosen q. Okay, well, is this any use? Well, if you go back to those papers that I mentioned, I'll make the slides available if anyone wants the references later. This is the key theorem that we have. Okay? Remember what we said we're trying to construct a surrogate approximation, UXP, and we want to guarantee that the energy norm of the error is bounded below some threshold. If I have that, then I know I stop my computation and it's accurate enough for whatever I want to do later in my UQ study. This looks a bit weird if you've not seen it before. So eta is the thing that you compute. It's a number, and that's the thing that you're going to use to base your decisions on about whether or not your approximation is good or not. So you compute eta. That's the thing that you actually want to know about. So the question is eta a good approximation for this? Well, results like this say, well, the true error is bounded above and below by some constant times the thing you've actually computed. So what you'd really like to know is how big are these constants? These are as good as your analysis, right? Sometimes you can get very tight bounds, sometimes the bounds are quite weak. And so for our problem, we spend a lot of time trying to understand how big these constants are and whether or not they're close to 1. So ideally, you want these constants to be close to 1 so that you can have confidence in this thing that you've computed eta, because that's the thing you're going to base your decision on. Is my approximation good enough now or not? Okay, so if you don't know how big these constants are or whether or not they're close to 1, you can't really have any confidence in that. You may be grossly underestimating your error, which is bad from an accuracy perspective, but you also might be grossly overestimating the error, which isn't necessarily bad from an accuracy point of view, but you might have done far too much work in order to get that estimate. So the couple of technical things here I won't focus on. There's a couple of constants in our analysis, so I'll skip that. The other important thing is, I said we don't just compute a number, eta. Our error estimate has two component parts, and individually those two component parts give us information. So remember, I choose this space y and I choose this space q. Okay, so let's say I've computed my initial approximation. I've computed eta. Eta is too big, so I now know that I need to do something else. I've got to now go back and enrich my approximation space somehow so that the surrogate model I can construct will actually be better. So the good news is the two pieces of my error estimator do more work for us. So if I wanted to, if I threw the functions in y into x, so made my finite element approximation better, I could compute a new approximation, a new surrogate approximation at the next stage. This says that this piece of my error estimator will give me a prediction of the reduction in the energy norm of the error that I'd get if I computed a new approximation in this space. I haven't done this yet, but it's telling me what the payoff is of doing that next. And that could be good news or it could be bad news. And similarly, if I was prepared to throw the functions in q into p and sort of do that at the next refinement step and compute this surrogate approximation, this part of the error estimator tells me what the payoff is of doing that. So what I can do is sort of test these things against each other. What's the largest prediction to the error reduction? Should I do a spatial refinement next, or should I enrich my polynomial, my parametric approximation? Sometimes they're equally big, of course. You might need to do both. But we get a way to help us make decisions in our computations. Okay, so I think I've got a couple of minutes to do some numerics. Okay, so those two theorems are really the thing that underpins this method. But you might have realized that at no point so far have I told you how to choose the spaces. Okay, I haven't told you how to choose x or y or p or q. And those theorems sort of hold regardless. Right? There's a couple of key assumptions that need to be satisfied, but there's lots of choice in the way that you choose these spaces. So what I'm going to do is sort of show you one sort of slightly negative result and then one positive result. So here's a problem. I'm sure we'll see these problems many times this week. So 2D on a square as usual, yeah. Right-hand side function. So here's the diffusion coefficient I've got in my elliptic PDE. Okay, and I'm going to do the usual crime and assume that these are uniform or associated with a uniform distribution. And then inside here, I've got some terms that are related to a particular spatial covariance function. Okay, so I'll come back to that in a minute. You may or may not know what's wrong with this problem. But I'm going to do what I just said. I'm going to start with a very low dimensional approximation space. Remember, I don't know before I start how many parameters I might need to put in here. So this is just my best guess. But I'm going to start low dimensional. So I'm going to start with a finite element space on a very coarse finite element mesh. It's just got h is equal to an eighth. And then I'm going to choose my polynomial space. It's just got two polynomials in it. So I've got the 0 index, so that just means 1. So I've got a constant polynomial. And then I've got a polynomial that's linear in the first parameter, and that's it. So I don't expect to get a very good approximation with this, but the idea is that's how I'm going to start my algorithm. And then I've got to estimate the error, so I've got to choose a y space and a q space. Okay, for the y space, right, so I'm not going to do anything very sophisticated. Let's say the only ability I have in my finite element code is to press refine of the mesh. So I'm going to choose y to correspond to doing one uniform mesh refinement. Okay? So if you know about Q1 finite element methods, then you know that. If not, don't worry about it. But then I've got to make a choice for Q. So what I'm going to do is I'm going to throw in another candidate set of polynomials in which, so this basically means in which up to 5 new parameters can become active. So my first polynomial space only has one active parameter. I'm going to throw in and test whether we need more, but I'm only going to activate up to 5 parameters more when I do this. And here's what we get. Okay, so press go. After making those choices, the algorithm just runs. We put in a finite error tolerance. Remember, this is what we're using. We want to ensure that at the end of the computation, our surrogate approximation to the solution of this PDE model satisfies some guaranteed accuracy. So it's a fairly coarse error tolerance here. My algorithm stops. And at the end of it, I've got an approximation that required, what's this, 1.6 million degrees of freedom. And it activated 19 parameters. So it decided that 19 parameters had to be active in the parametric part of my approximation space. So if we start with this plot first, so this is the number of degrees of freedom. We've got 1 dot for each step in the adaptive routine. So I guess it's like maybe a dozen adaptive steps. Here's the energy error. So the black reference. So obviously we don't know the true solution, but we can kill the computer and get sort of a fake true solution. This is where the error should be, but the pink is what the algorithm is actually computing. Okay? So initially, so this is what we call the effectivity index. So the effectivity index is the ratio of the true error to the estimated error. Remember, our theorems have some constants in them. If our constants are close to 1, this should be close to 1. Okay? So on the first steps of the algorithm, the error estimator is actually doing an okay job. These lines are close to each other, but over the course of the algorithm, something goes wrong. We lose the accuracy. Our error estimator is a less good approximation of the error over later steps of the algorithm. So why is this? This is because for this problem, the terms in the diffusion coefficient are decaying very, very slowly, and our choice of Q was not good enough for this scenario. Here's another problem, which you can contrast with. So it's a different diffusion coefficient. The terms here decay at this rate. You may see this problem later in the week as well. Okay, so this is a bit nicer than the problem that I just showed you in this respect. But I'm going to initialize the algorithm the exact same way, and this is the output. Okay, so final degrees of freedom, much smaller. Number of activated parameters, much lower. Because in this problem, I need fewer parameters to estimate my quantity of interest to the same error tolerance. The algorithm learned that. And here you can see that actually the effectivity indices, they hop around a bit, but they're close to 1. So on all steps of the algorithm, we're getting good agreement between, well, the fake true error and the estimated error. Okay, so Fabio's telling me I've run out of time, is that right? So I'll just give you a quick announcement for a poster. So what I've told you up to this point can be implemented with sort of whatever choices of finite element spaces and polynomial spaces you have lying around. So you definitely encounter issues like this if you don't pay attention to your choice of spaces and how they're related to the problems that you want to solve. But one thing that we can do is move from this very simple setting where the approximation, the surrogate that we're looking for, just lives in the tensor product of two spaces. We can actually get much better convergence rates if we go to something called a multilevel approximation. So I'll invite you to go and look at Adam's poster to know more of the gory details. And I will just show you this, the payoff that you can get by moving from a single level algorithm to the multi-level algorithm. So that's the result I just showed you. If I move to a multi-level implementation, same story, same error tolerance, we can achieve it with far fewer degrees of freedom. Okay? So why is this? This is essentially because we're allowed to use different finite element meshes for different terms in the approximation. And we can actually get sort of the optimal, the predicted rate of convergence using these methods. So I've run out of time. Those are my final bullet points. So ultimately what you get, this is the kind of point I was trying to make, these simple, very simple physical elliptic PDE models. If you do this kind of thing, it's quite complicated, but you can, at the end of the day, if you go through the pain of it, guarantee that you get an approximation that satisfies a certain error threshold. And ultimately, that's what numerical analysis is all about. We do have a version of this code, mainly curated by David Sylvester. So I encourage you to look at his webpage if you want to download the code. It's in MATLAB for a simple implementation of what I talked about. And in the remaining slides, there's lots of references. So if you want to know more about this topic, then I'm happy to make the slides available. Up there.
Minutes for questions before lunch. Start with one and break the ice. Actually, I have two. One is the thing you mentioned at the end is multi-level version. How much more complex is the implementation? Because this means that for any polynomial chaos mode, you have to consider a different finite element grid and so on.
It's true. It's not trivial. It's not straightforward. And a key thing is that you lose this simple Kronecker structure in the linear algebra. So the linear algebra is definitely much more of a headache when you have this simple tensor product space. So that goes out the window. But I had a PhD student who's very good and very persistent, and it's definitely not trivial, but it can be done. That's all I will say.
Yes. So I'm interested in the part about intrusive models or surrogates. So can you quantify roughly how much you gain by entering the modeling, by being so intrusive? And is there any relationship between the how much you gain in the theorem you wrote down in terms of error, or is there more or less benefit depending on the PDE you're looking at?
Can I ask you a question first? What do you mean when you say intrusive?
By using you're using actually the equation. I belong to the world of
But
black
some people
box.
I've talked to say intrusive means I have to go and modify my code, and some people say intrusive just means I need to know what my PDEs are. So which is it?
The PDE.
Well, if you don't even know what your PDEs are, then you've got no hope of doing this. You've got no hope of doing this.
So you must benefit from it.
Of course you do. So what you want to look at is your error analysis. You need error analysis. For simple elliptic PDEs, well, okay, is there a short answer to this question? If you have a modest number of parameters, you get much more accurate answers more quickly with the stochastic Galerkin method. But the key thing is the size of the problem that you have to solve. So in this problem I showed with 20 parameters, right here, wherever it was, sorry, I think I've lost it. right here, if you can't even do this, then no, right? And the more parameters you have, the quicker the larger this number will be. But then that's why you need adaptivity. I guess the point we're trying to make is, with an adaptive algorithm, you can actually do this. But have I done the comparison against a simple sort of Monte Carlo method? I haven't. Probably other people have. Does anybody want to jump in here? I mean, if you fix a number of parameters before you start, you can find papers that do this comparison. But what's a fair comparison? That's one dialogue we're supposed to be having here. What's a fair comparison? We should never compare this against a basic Monte Carlo method, because that's not a fair comparison. I might be able to use a multi-level Monte Carlo finite element method. It depends on the structure of my problem, whether I have a hierarchy of meshes. So for problems like this with a modest number of parameters, this beats Monte Carlo for sure. But there's a threshold where the number of parameters tips it in the favor of another method. So if you have input random fields with very small correlation lengths and you need a large number of parameters to represent those random fields, it's very tough to do this with a basic method. Can you do it with an adaptive method? Probably, yes. We had problems with infinitely many parameters in theory here. And we showed that using this method you can get estimates which, we pick the tolerance for the error. That's what you want, right? The method does it for you and decides how many parameters are important. But it's highly dependent on your quantity of interest. The energy norm of the error, probably, I've talked to engineers, they're not really interested in this as a quantity of interest. It's something else they want to control. Having a fully adaptive algorithm that can work for any quantity of interest, I don't know about that. Can be done? Well, any measure that can be written in terms of the energy error, yes, we're trying to do that and do other things. You can use adjoint methods and things like that, but they're absolutely not black box, for sure, which I guess is what you want. There's more work to do.
Just two quick questions, hopefully. Just in slide 10, you show this the stochastic Galerkin method, let's say formulation. I'm not familiar with it, but it seems to me just like the standard Galerkin method marginalized over the space of parameters.
Standard Galerkin method, you just integrate over your parameter domain with respect to some measure that you've picked that's appropriate for your problem.
And
no, sorry, it's not.
Functions are stochastic. You have the full.
The function space here, so if you're familiar with Galerkin approximation standard problems, the only thing that's different is your test space and trial space, solution space. They're not just functions of your spatial coordinates. This space is a set of functions that depend both on the spatial coordinates and the parameters.
But you choose a Kronecker structure afterward, so they are separated.
Okay, so probably so this is isomorphic to the tensor product of this L2 space on gamma with this H1 space on D. And then what we do is we work on each part separately, if you like.
So, but under that kind of this it's not just a marginalization. You say it's not, even if you separate space from parameter. Then
I don't view it that way.
Because the way I see your gamma, the integration there will just run over your functions that have dependence on the parameters, and the
I'm not integrating anything out. I don't. That's what you mean.
Okay. Maybe I should. Yeah. Then I'll ask you later about what it is. And the other thing is, in slide 18, you choose these polynomials on 20 dimensions, and I understand we need polynomials for the error bounds and for the proofs.
This is what I've been to illustrate, but this is a naive choice.
Yeah.
This is a naive choice.
The question is, but you always mention polynomials, nevertheless.
Yeah.
So the question is it just because you need to prove and to get expressions for your error bounds, or there is any other reason why you will do polynomial in such a huge dimensional space?
Okay. Well, look, the dimensions is out of my control, right? That's what's in the problem.
Yeah.
So, why are polynomials a good idea? We know for elliptic PDEs, right, not my work, many of the people in the room, that we know the solution to elliptic PDE is a really nice function of those parameters. It's a smooth function of those parameters. So if something is very smooth, it's a good idea to to sort of approximate it using a polynomial. If you think about polynomial approximation in 1D, if the function you're trying to approximate has as many bounded derivatives as you like, you're going to estimate it by a polynomial, and you increase the dimension, the degree of the polynomial, you'd expect to get better and better accuracy.
Use like radial basis functions, or
You
any
can
other
use
kind
other
of
types of basis functions. So, yeah, I'm not saying you shouldn't use other types of basis functions. But polynomials that are globally defined on the parameter domain, we can do it for elliptic problems because of these issues. For other problems, that's not the case. If you have solutions which are not smooth as functions of these parameters, you wouldn't do this. Or you'd use some locally adapted polynomials on a mesh on your parameter domain if that were possible. But the thing, the choice of basis functions is important as well. We use orthogonal polynomials precisely because it gets us sparsity in the linear system. So when it comes to actually solving this linear system, wherever it was, we get sparsity from this. This particular choice buys us sparsity. That's why we like it.
So if I summarize what it says, one side because we need to have expression for our error bound, and the other side because we want to ensure sparsity on the linear algebra problem.
I guess, yes, we have error bounds for this particular choice.
Yeah.
It's not to say you can't get error bounds for some other choice,
Okay.
but when you have smoothness, polynomial approximation is usually quite good. It's the same with finite elements. It's a choice between the H refinement and P refinement.
We know you put it there, right? For high dimensional spaces, it's definitely, if you have smooth, you will choose all the bases to the approximation, not polynomials, because the space of polynomial grows like horribly on so many dimensions, right? This m plus d taken from d, and the basis size is huge, right? It grows very badly.
If you do it naively,
exactly,
in the adaptive routine, the algorithm was choosing the polynomials to use itself. Well, according to what we coded, right? But it was deciding which polynomials were most important by estimating the error reduction that you get by incorporating that polynomial into your space. So you estimate the error according to the polynomial space that you have. So you can add in a candidate set of polynomials.
I think this is a good topic for further
But
discussion.
to just one point, if the polynomials are not needed to accurately estimate your quantity of interest, then they're not used. Here, you use no information about the problem. It's a completely naive choice. There's probably 8,000 of those polynomials were not necessary to include in your approximation space to get what you needed. That's what adaptivity does.
Last question.
In your PDE, the uncertainty came in via this coefficient function A. The function on the right-hand side, f and g, were deterministic. Can you extend your method to the case where f and g is also subject to uncertainty?
People say yes. You can do f. You have to be careful that any assumptions that you need for the problem to be well posed are respected. So you can't just stick arbitrary choices of random variables on the left and the right-hand side and expect everything to be okay. For uniform random variables on the left and right-hand side, it's okay. But for instance, if you stick Gaussian on the right, you can end up in trouble. So in theory, it's okay as long as you respect the assumptions that you need to be respected or to get a solution. So yes, in theory, the methodology can be applied. The adaptive, we haven't. For the adaptive part, we haven't done anything with that kind of thing.
Not only well posted, but also your adaptive refinement strategy is working.
No, it wouldn't. No, I haven't thought about it.
Okay. Up here, so we thank again, Catherine.